In this video, I want to have a look at binomial theorem. So the binomial theorem is based on the fact that the numbers in the rows of Pascal's triangle are actually the same as the number of possible combinations of R objects from a total of N objects. So that's our combinations. So for example, if we consider this row here in Pascal's triangle, so we've got 1, 6, 15, 20, 15, 6, 1. If we were to have a look at the combinations from 6 objects, the number of possible combinations of 0 objects from a total of 6 would be 1. The total number of combinations of 1 object from a total of 6 would be 6. If we were choosing 2 objects from 6 objects, there'd be 15 ways we could do that. So these numbers work out to be the same as that row in Pascal's triangle. What I've written just underneath is that same second row, but in the other notation we have for our combinations. Now, just off to the side here, I've just written a reminder of what these mean. So those two notations are exactly the same. And to figure those out without a calculator, we'd be doing n factorial over r factorial n minus r factorial. So what that means is that we no longer need to have Pascal's triangle drawn out to be able to figure out our binomial expansions. Instead, we can write it out as this here. So we know that our powers of x, or that first term, are decreasing as we move along each term. The powers of that second term are increasing as we move along. And then we can use our combinations to find our coefficients rather than Pascal's triangle. So I want to have a look first at just a simple expansion. So we're asked to expand 2 plus x all to the power of 5. So we're going to go through and use that combination notation. So we're going to start with 5, 0. Now, it doesn't matter which one I use, whether the x starts to the 5 and 2 to the 0, or whether it's the other way around. And the reason it doesn't matter is because those combinations are symmetrical. Okay, so 1 starts at the highest, 1 starts at 0, and then we move our way along. So then we've got 5, 1, x to the 4, 2 to the 1, plus 5, 2, x cubed, 2 squared, 5, 3, x to the 4, nope, hang on, sorry, the x's are going down, x squared 2 cubed, plus 5, 4, x to the power of 1, 2 to the power of 4, and 5, 5, x to the power of 0, and 2 to the power of 5. So then I can go through and work all those out and simplify them down. I'm just going to end up with x to the power of 5, plus 10x to the power of 4, plus 40x cubed, plus 80x squared, plus 80x, plus 32. Okay, so going through and using those combinations rather than Pascal's triangle. In our second example, we want to evaluate the coefficient of x to the power of 9 in the expansion of 3 minus x all to the power of 12. So the term that's going to involve our x to the power of 9 would be when we have 12 from that power, and then 9. Then I'm going to have minus x, because that negative has to stay with it, to the power of 9. And then it's going to be my 3 to the power of 12 minus 9. So whatever the opposite is to make it up to that 12. Okay, so that means that's the whole term with that x to the power of 9 in there. That means the coefficient is going to be, if I had 12c9, and then minus 1 to the power of 9, because we're not counting that x to the power of 9 because we just want the coefficient. And then 3 to the power of 3. Okay, and if we go through and work that out, we would end up with minus 5,940 as the coefficient of x to the power of 9. So that's having a look at two examples of the binomial theorem.